Okay, everyone, this is round two. We're going to cover some of the information that we presented during the earlier session. The earlier session that we had was for the DISA Technology and Emergency Management team and Emerging Technologies Management. And what we were doing was we were responding to a request that they had for us from the last time when Invisinet was here doing a technical presentation where what the role of emerging management was to identify technologies that had merit and utility within inside of the DISA workforce. And from the original presentation, they described what their technology was, but then they reached back out to say, where are you now? And what advancements and what progress have we been made? So from my area, we look at the things called the technical readiness levels and being able to evolve beyond proof of concepts to operational field testing to product validation to the point where you start getting into the level where you start moving between TRL, which is called technical readiness levels, level 6, to level 7, where you begin the processes of doing real live implementations, field tests, getting user feedback, and those areas. So the Black Pearl has actually we've been working with DISA now for over a year in the process of developing technologies that can be able to be used in training episodes and moving us through to the process where we can go into the implementation and the proof of concept. So some of the people here that are in this room have been instrumental in helping us to get to that level by being able to start shepherding and fielding, doing the documentation behind some of our programs, and preparing the paperwork that we need for DISA as a sponsor of SecureXperts moving forward. So what we're going to do is I'm here with Brendan Sullivan of Invisinet. And what we've done is we've created an integration where we're using the combination of the NSA commercial solutions for classified capabilities to intertwine them with mission critical and mission focus areas that can be used that extend not only into DoD classified spaces, but being able to start leveraging the point where Cyber Command can have better control over IT, OT, and ICS devices with an additional layer, which we want to call it a layering approach, to extend CIFC to a different level. So what we're going to talk about is how do you extend zero trust network architectures over commercial solutions for classified capabilities? And then we're going to give you a little bit more use cases. The earlier presentation, we were more like talking about the technology, but this one's more about showing you guys how it works. So Brendan and I will kind of get into it, but we're going to start by talking about Invisinet. And as we went through the processes of where we are now, we're in the processes of being able to prepare ourselves for technical validation, where we're seeking to expand our product solutions into POCs and use cases. There's 2 use cases that we currently have that we're going to describe today, but one of the areas that I've seen some capabilities to enter that we'll talk about today is the use of our implementations into seaports. The other application that we already are looking at is working with a training program that we're using for what's called DoD Cyber Workforce Development, being able to build capabilities for being able to increase training where they don't have to traditionally go into a SCIF environment to learn about cyber network exploitation and cyber network effects, as they call it in the DoD. So what's brought us together is we believe that we can add additional layers of security to existing technologies that are currently approved and aware of by and approved by the NSA. And we started with a technical presentation where we launched our first introduction of the Trusted Integrator Training Workshop at the NSA Commercial Solutions for Classified Conference in May, last month. So now we're moving forward as we start combining and integrating our technologies with the SecureXperts Black Pearl and the Invisinet. And what we're going to do is we're going to take you through kind of an experience to go from where the identity credentialing and access management of users then start flowing in to the adaptation of how the Black Pearl controls communications, and then how the zero trust network architectures are extended by Invisinet and their capabilities. So the first thing we wanted to talk about real briefly, not to be verbose, but the Black Pearl is known as an end user device. It's called an untrusted device that connects to secure networks. So what happens is that we build these devices and we apply certain standards and requirements that are required by the NSA to being able to prove that this device is secure, but as it participates on a DoD network, it's considered to be untrusted. So NSA has been through the process of using approved hardware and software. And then as we move through, we have different kinds of components that are required by the NSA to being able to make sure that we're able to build the capabilities in order for it to be approved for being able to send data through what's called a gray network. And a gray network, we'll kind of go into a few of the diagrams before, but I wanted to start with a little bit of the definitions. The Black Pearl is an end user device, but you have a thing called the wireless LAN component, which enables the Black Pearl to communicate classified information, and it attaches to what's called a gray network and then gray network management services. Gray networks are supposed to be the areas that protect the information flow from an access point and a continuous monitoring approach. And this model that I have on the screen is a delineation and a very quick definition of what happens in a CIFC network. You have an independent site, and the Black Pearl operates as a black transport layer, but it goes through what's called an outer encryption component, and it connects to what's known as gray network management services. These gray network management services control the flow of information between a classified network and an unclassified device. And the gray networks provide the level of authentication and level of security to build what's called a tunneling approach that is going to be able to protect the data from any form of device out in the field using secure LTE transports to get to red networks, which is traditionally classified information inside of a DoD network. So with that being said, I'm going to turn it over to Brendan so that he can give a little bit of a definition and to give you an understanding of the components that are in the Invisinet component. Go ahead, Brendan.
Well, good afternoon. I'm Brendan Sullivan. I'm the CEO of Invisinet. Most of you guys I've met and kind of given the theory of Invisinet once before, so I will spend less time on that this go around and a little bit more time on practical implementation and the demo. But Invisinet, for those that haven't heard of us, we were actually developed 15 years ago for the Department of Defense. And at the time, using IRAD, military research, first for the DoD and then later for the Army, we developed a technology. The problem they were trying to solve is by 2012, we had troops in Afghanistan with their own personal cell phones. And by just mining public infrastructure for them connecting to Zoom home or just cleaning up the towers, you can get pretty accurate troop movements, troop strength. So the question was, hey, is there any way to build secure enclaves over the internet and make that traffic flow into the period? And the answer is yes. So we developed a technology where we could take trusted identity and then encapsulate it into a token that we hide inside the IP packets. Right? And then once we do that and we pass it end to end, it'll survive any kind of network hop, doesn't matter what kind of transport layer it is. We then, on a gateway on the other side, because it now can read trusted identity at a great amount of detail, that can be used in real time to not only hide protected resources, but to overlay those networks with all sorts of forms of microsegmentation and identity and access controls. So think about this in the CIFC space as, a fifth layer of hidden audit trail, hidden protection. And particularly for the edge of your network trying to connect the green to the black, where you're on really ugly, messy networks, right? So the use cases we're going to talk about, we're going to talk about things. So what we'll talk about is how lightweight this technology is. So, by itself, the 60 standard doesn't require Invisinet. These machines are incredibly hardened but they're incredibly beefy. Both, it needs a lot of hardware and a lot to run this software at this level of security. Invisinet lets us extend that boundary in a super low compute, low overhead for something like satellite communication. So we'll talk about how that's good for kind of SCADA control and protecting like a military base from getting your HVAC system hacked.
Or in areas that don't have the same level of connectivity that you would have in most urban areas.
Yeah.
It's used for rural deployments, tactical deployments,
You're
drone.
getting a third-party maintenance guy to come out and work on a device out in the middle of nowhere, and you want to make sure he's exactly what he says and he's not a Chinese spy eavesdropping on your network. That's a very good use case. And then lifetime extension, so you can do this on old hardware that's even solar powered without filling the battery. And then on fast-moving mobile assets. So the maritime one, you think about drones, you need something very lightweight because you can't have the security layer killing the battery on the drone.
That's right.
So we'll go through both those use cases. And so that was what Invisinet was originally designed to do. We went through all 9 levels of technical readiness. By 2018, we're on the DoD's ACAL, and then we redesigned the product. But back then, it was very hardware-based. We moved it to entirely software-based, and then we beefed it up to have iPad clients and then all forms of cloud, right? So how you have to do virtual switching to cloud required a lot of extensions, and then we relaunched the product about a year ago, and then re-entered the DoD space. Our architecture is pretty straightforward. You need something on both ends, A and Z. And you can mix and match them depending on if the endpoint is a human being or the endpoint thing. We start on the A end with a thing called an InvisiPoint agent. So what happens is you push out your mobile software through a secure mobile device manager, and you install the agent that is on a laptop, a tablet, a phone. Your vendors would install it from your DoD store, if you will. And then we go through a special one-time activation, using things like the PIV cards, where we check the certifications and the identity of that person, make sure that machine is exactly who they say they are. And then we do a one-time provisioning that starts generating these tokens that have your tokenized identity that we stuff in the headers. Then on the other side, we have a gateway. It's all virtualized. So you put that in your DMZ, you put it in front of whatever you're trying to hide or whatever you're trying to protect. And that is the policy server that is receiving and reading those tokens and invalidating them, in a certain algorithm to make sure that you're protecting the other side. What an enforcer is, so that gets you from, the laptop to the DMZ. But in anybody's private or public data center, there's a heck of a lot of computer gear that sits between the public side of your DMZ where you're cloaking and a secure database that's 6 security zones deeper, multiple DMZs deeper. So there, on an enforcer, you would run, again, that agent, that driver shim, directly on the protected resource, the database at the network layer. And it can do two-way protection, and it talks to this controller one-to-many so that it can apply the rules in real time. And then when you chain this all together, it looks like this. So we suck in identity from trusted sources in the one-time provisioning, right? And then we check every 10 minutes that your trust levels haven't been changed. So it's all about generating a token and passing it through these gateways. So we have a wide, whether it's Okta and multi-factor, and you use those lots of certs, or you're using Active Directory and 509 certs, or you're using WidePoint through Ziva to get to the PIV cards, and that's what we integrated into the Black Pearl. That's how we're checking identity. So we're not originating identity. You would manage it in the identities and lifecycle management systems, but we're tokenizing it and managing it after that.
That's correct.
And then downstream for continuous monitoring, a major pillar of all forms of zero trust, We integrate to any kind of SIM or modern SIM or intrusion detection system because every component is real time, encrypted syslogging every event out to that. So once you stuff, trusted identity inside of every single packet, your downstream systems can get much, much more intelligent as far as false indicated with confidence for yourself.
And one of the things that we are looking at is mostly when you start talking about visibility and enforcement, you're dealing with the IT side of networks, which is identity management, identity provisions, roles and realms to specifically like data and other kinds of information. The Invisinet application uses integrations with IT, OT, and industrial control system devices that is kind of like the next phase of where vulnerability management occurs in the future, where it's just not just the identity of the data that's going through a network, but the identity of objects that are field deployable. And as we know that IT and OT devices represent the next generation where our highest level vulnerabilities exist.
Our system does not care if you're a thing or person. They're all identity sets. Obviously, how you validate the identity works differently for things versus people.
That's correct.
But what you want to do in the latest reference architecture Zero Trust, where this is all going in the next 2 years, is you really want to be running this at all 3 levels simultaneously. You want to keep your application security layers that you've had with groups and policies. You want to add to that independently at the data loss prevention layer, DLP that's checking identity at the field level of data and encrypting the heck out of that, or video.
That's right.
And totally independently running with a different scheme and control system. You want to be doing that at the network layer. You want all 3 of these things going into an AI-backed SIM, Security Information Management System, your ITDR. And they should triangulate at all times in real time. So it should always say, hey, this is Brendan Sullivan's Mac trying to access this really restricted database. And all 3 layers should say the exact same thing. If they don't, you've got a major indicator of compromise and you've got a problem. So that's the name of the game. We're going to, in this demo, just show it to you we stripped out all the other layers to just focus on what happens at the network layer. But that's the name of the game.
So hold up, before we do this, so we're just going to talk a little bit about the ID components. We have the PIV and the CAT component. Where's Mike Horkey? Is he still here? Why did he step out at the right point? Okay, so what we're going to do is we're going to take a quick point about the identity management and the provisioning standpoint. With most IT, OT, and ICS environments, you typically don't have DoD credentialed people who are performing third-party support for these field-deployed IT devices. So what the use case is that SecureXperts has for the Invisinet and the Black Pearl applications is a defense hospital, where we have IT, OT, and ICS devices that are connected to the government network. But these third-party contractors that don't have to go on site to provide for the repair and the maintenance, they go in and they log in securely into the network. So by being able to protect the IP-enabled devices that are on the end using Invisinet gives us the ability to issue the credentialing process to the individuals who are getting access from third-party off-premise locations that are compliant with DoD policy for remote access. So in the absence of Mike Horkey not being here, we're just going to talk just a little bit about the identity management and the provisioning process, that when a user goes through strong identity proofing, they're assigned credentials, one for network access, any others encryption and digital signing, which are all added into the framework of us being able to authenticate these users onto these platforms. So that being said, it doesn't matter whether you're using the Active Directory or the PIV and CAT card, but we wanted to enforce multi-factor authentication, where what we can do is we can embed certificates and perform certificate revocation, not only of the users, if there's a contractor A that gets transitions to contractor B for a contract, then that person then could be revoked as an organizational unit or being able to be transferred. So, Mike, what we were talking about was the strong identity proofing. And what we have over here is we have an identity management kiosk where the users don't have to go in front of an adjudicator. They can go to a specific location and they can be enrolled from a geographically disparate location to being able to get access to the Invisinet platform. Just wanted to add that. Want me to go to the next one?
Yeah, so this is about as deep technical as I'm gonna get until we get into the demo.
Well, yeah, because we're going to jump into the demo.
But I just wanted to explain what's happening and how cloaking works. So we go through a one-time activation process to bind the agent to your machine and make sure that you're who you say you are. So you know, your department has some kind of mobile device manager or store, downloads the agent, and then you put your credentials in, it goes through a one-time activation. When that laptop for the very first time hits the edge of the network, anywhere on the edge of the network, it will start activating this product that's running hidden in the background on your machine. And it starts generating these pool keys. So we actually generate a 64-bit key every millisecond. So for every user or sensor, there's this constantly generating key pool over here where we're sharing the 32-bit, public key part of it. Now on the gateways everywhere, they have also a synchronized key pool. If you did not put any kind of sharing, if you never connected back to your main controller, your gray network, these things could run in an unconnected air-gapped enclave for about 2 years before they would desynchronize. Okay, of course you'd want to check in more often to make sure, trust levels haven't changed. In fact, we check in about every 10 minutes. Right. But this will run for a very long time, even in air-gapped systems, independently, and it's a massively distributed system. So the tokens are tokenized and it contains your identity. And then what we do is when you open a computer session from your NIC card, and I'll show you there, we actually replace the 32-bit random sequence number of your session with this token. That's where it's hidden. It's hidden inside a 32-bit random number as a 32-bit not so random number. And then when it hits the other side, it checks that key pool and either passes the traffic or it doesn't, and then it immediately deactivates that token. It's a one-time hash token. And then every 4 to 8 seconds, depending on the latency of your network, it will re-verify using a different handshake of tokens every 4 seconds. Every 10 minutes, it'll check back with your secured server about your trust levels. And if somebody is on watch list or changed, suddenly things they had access to 10 minutes ago could disappear on them. We can actually reroute their traffic mid-session into a honey trap if their credentials change.
So now I think what we're going to do is we're going to move to a demo. It's the demo team.
One more slide on cloaking. So that's access, and I'm just going to show you this. So the one thing that makes it unique is actually how it cloaks. So other people talk about hiding packets, identity packet for access reasons, but nobody really does what this does except for us. So when you open a session, there's a 3-way handshake. That's just to connect a client to a server. Yeah. Oh. So so when you open any kind of TCP/IP session, there's this 3-way handshake, right? It's set from the client to the server. You send a synchronization packet. That's when you generate the randomly generated packet header number and then increment it with one after that. It's also where you define the window size and then the server on the other side acknowledges, yes, I actually exist. Here's my information, and they shake hands. Then you connect the connection, right? This is the bearer path. If you're using any kind of authentication at layer 7, the app layer, like I'll just use Cisco AnyConnect VPN. This is the signature of the key handshake for Cisco, this 4-way handshake. So if your network is being scanned by a bad actor 100,000 times a month, which every network out there is, what they're doing is they're using programmatic bots that are looking for this signature. They're scanning every single IP address in your network. And then they can see, you could plug this in a chat GPT and they'll say, hey, that's a Cisco VPN. And immediately it can look up the known exploit database and then just try a brute force attack. And if you have bad hygiene or you make any kind of IT mistake, they're in. The reason why ours can cloak is we actually do this right here. So the injection is done in the very first synchronization packet. It's called first packet authentication. We stuff the token in there. It's looking for it on the other side. If anything, and I mean anything coming into that network is missing the token, or it's a dead or invalidated token, not only does it block the traffic, it black holes it. So no matter how you scan that thing, it'll respond with host must be down, IP address invalid, session timeout. It's playing dead. And what that does is confuse the spectral analyzer to drop you off the target. Okay, that's effectively how it goes. And that's the name of the game. And then because you're literally going from the first packet on the NIC card to the first packet of the session on the secure database, if you want to run it all the way at the database server level and it can block it, there is no way, one, for the bad guy to know this is running in the background because it's hidden. And secondly, there's no way to get a man-in-the-middle attack. Because the token's one time and immediately invalidated, if you try to hit it with a replay attack, it also will block that. This is using standard, yeah, so we have a lot of patents on first packet authentication, but we are using standard TCP/IP protocol. Yes, yeah, this is a very standard handshake of any TCP/IP setting, session setting. There's nothing private. Now all sessions are connected. We can do it in UDP as well, but this is the TCP handshake. Okay, so even bully protocols, we can do this inside of it. It works a little different. The game there is then, MITRE will tell you, network reconnaissance is a nuisance, but there's nothing you can do about it. We completely disagree. You absolutely can block reconnaissance. So even inside your own secure data center, you're running things like Nessus scanners looking for intruders. Unless you authorize the Nessus scanner to generate tokens, and Doug's going to demonstrate this, it will block your own Nessus scanner through every hop you know. And so it doesn't have to just be cloaking on public infrastructure. You can cloak it in every segment of your network from any kind of unauthorized scan. Okay, and by doing that, you try to stop them before they can reconnaissance, then they can get into your network and map it. That's the name of the game. And because we're outputting every single one of those hops along the way, it creates an amazing, very detailed map of how people traverse your network. Okay, for the kind of insider threat detection and blocking. Okay, so with that, I think we'll go to a demo. Again, this is just MITRE. This is the part of the MITRE attack framework. The very beginning, we're trying to block the most common ways you profile a network to break into it. We stop it there. Okay, so I'm going to hand this off to Doug, sitting over here on the couch. Yeah, that's fine. So he's stealing the hardwired cable.
Yeah, so we, as no good demos have any hiccups, realize that we cannot be on Teams to share and connect to this infrastructure at the same time. So, so I'm going to show you this live. Teams comes up, which it should. There we go. All right. Okay, so the way I've simulated set up here is two different Kali Linux clients. Now these are on the same subnet. They're actually adjacent to each other, same vSwitch. They're built the same way. You'll notice that one is blue on the left, the other's black on the right. I'm going to jump back and forth a little overlap just because this is my laptop, so it's so small. But what we've done is just taken a few kind of common attacks, reconnaissance, and just going to show how we block it. What's important to note is that none of this is being done by IP. We are topography independent. Everything is being done by identity. On the left-hand side, the blue machine, you will see that this right here is tied to an identity that is linked to Brendan's cat card. He is the good guy. We trust him. He looks better than me. On the right is me. My cat card can't do anything. I'm not trusted. And I created this little menu. This is just for the purpose of demos. It just takes a combination of command line variables to make it easier to run. But we can show you that if you want to see it.
Yeah, if I can just jump in here for a second, just so you know, and there's a drawing in your packet. The one gateway is running right here on this black pearl, and then the receiving gateway is running right there on that little device. And then he's generating tokens from his laptop, passing Series 2 gateway. We put on one side of this network 3 different versions of Kali Linux to do this demo. 2 of them are authorized with different permission levels to get to different parts of the network, and one was the bad guy. Right? So the black Kali background is the bad guy. He's not authorized. And so that'll invoke the poking, and then the good guy, you'll see what he can do. All right, take it from there.
I have a loud voice and I'm gonna sit down so I do not block anyone from seeing. All right. So usually I would jump back to one of Brendan's slides, but I will just talk to it. So I like to start off with the MITRE attack framework. And if you start in the first pillar on the left-hand side, you'll see a bunch of different reconnaissance attacks. One of the value props that I like about our technology is that I don't really need to worry about which one of those attacks they are. I don't need to worry if new attacks come in. Because of how we work, it doesn't matter how you execute your reconnaissance attack, we will block it. So it can be 1 or 2 of those things. It can be 20 of those things. We will deal with them all the same way, which means we don't need to know about every type of reconnaissance attack. The way we do it, if something new comes in, we will protect against it. Now, the way I usually like to walk through is, so these 2 machines are adjacent to each other. They would be 2 operators that are sitting next to each other. So on the left-hand side, we have Brendan. On the right-hand side, we have Doug. We just got back from coffee and we try to see what's going on. Now, the network discovery button is based on ICMP. It takes a bit of time, so I'm just going to type in a ping right here, just so we don't have to wait for timeouts, and I'll explain why that is the case. So we see on the left-hand side, we're getting pings. On the right-hand side, we don't. Now, with the network discovery that actually goes through an entire class C, which is the /24, we'd have to wait for every single system to timeout to give us our feedback, which is kind of a pain. So in this scenario, I'm just running this, but what our devices do is they can block at the ICMP level if you need to. Not everybody wants to. We recommend it, but we also recognize that quite a few network management systems do their inventory and heart beating based on ICMP. So what we've done is given the ability to lock in and say ICMP traffic can come from a certain device on your environment. Now, we'll talk a lot about identity. For those of you that know ICMP really well, know that's not really a protocol that was designed to inherit identity. So it operates a little bit differently. So that's why we talk about it as a protocol. We can protect ICMP, either allow it or disallow it based on where it comes from. So if you've got that one NMS system, say you still believe in IBM Tivoli, you can be using that. We can allow for it or not, and then block everything else. Now, right now we see that our malicious actor has not been able to get anything. He doesn't know what's out there. All right. He just says, all right, I'm looking at a network. I don't see anything. The right-hand side, we do see something. We're seeing some responses back. What the technology does is because we drop at the identity level, at the session establishment, we allow for the resources that we're protecting to do their job. They don't take any kind of computational hit, and we don't provide any feedback. If you notice on the right-hand side, these are the types of responses you get back from a normal ping command. All right, we're not inserting anything that says Invisigate blocked your ping. This is what you get back from the ping command. And as we go through what I'm going to show, every single feedback will be from the application or protocol. Nothing comes from us. So, Brendan had mentioned a Cisco, firewall. So let's say you're using an ASA. If you get some kind of feedback that says Cisco blocked you, you can then start going off and looking up Cisco. Mentioned look at the vulnerabilities database. We don't give you anything back. So even knowing that Cisco firewall there gives an attacker a step up, they don't get that with us. Whether Cisco's there or not, doesn't matter. And as Brendan mentioned, since we're protocols based, any other control that allows your network to function can be in play. We will work with everything. So now
there's nothing but a cable between the two boxes, right? And yes, the VM could have a virtual firewall and a virtual switch and set up a path, but we've enabled nothing but actually using the identity token to create this result.
So now walking through our attacker, let's assume that somebody, that is trying to scope something out. They now see on the left-hand side that they've got, some traffic coming back. On the right-hand side, they have nothing. I'm going to jump to the port scan. So let's see what comes back. So I'm going to click on my little port scan button on both of these. And what this is doing is running an Nmap. Now, on the left-hand side, it came back a little faster because you'll notice that the feedback you get back from an Nmap is what the application would normally give you. It says that nothing came back. It helps if I actually take out the word IP and scan the right host. All right, so one IP was scanned, but nothing came back. All right, it's the same IP that we're going to see on the other side, but I didn't get any feedback. It may not be there. I don't know what's running on it. Now, on the left-hand side, we switch back here, we see that we got some feedback. We were able to identify that two ports are open, SSH and HTTP. Now, if I'm somewhat, capable techie, I'm going to assume I've hit a web server. All right, fairly straightforward. So then I would probably try and see, okay, if I have the web application running, and I might try and see what I could hit. So now if I go from my left-hand side, and I just plug in the IP address of our resource, I get a website. Now, this is a dummy website I created, but this could be anything. This could be a website that you create. This could be any TCP application that you've got, a client connection for an application, something you built custom, a controller for video feeds. Yeah, they beat you to it. So because I knew where you were going. Now, on this, just for completion, we're going to do the same website over on our other system. All right. And what's going to happen is, as long as it takes for our web browser to decide I've tried hard long enough, it's not there, is what is going to give you that feedback. And you'll see the feedback here doesn't come from Invisinet. The Nmap failure didn't come from us. The ping failure didn't come from us. They came from the protocols and the applications. There's no feedback whatsoever. That's what we call cloaking. You don't know that something's there, that you don't have the access to it. You don't get username and password in bad combination. You get nothing back. But we see that the application was doing its job, and for anybody that had identity, they could interact with it normally.
Yeah.
Go for it. The block?
Yeah. So it's working because every single session that's connected to that gateway is technically valid. So as long as they keep coming about that block will never be able. Yeah. So continue whatever you said. So what happens is it's a one-time, so we're generating a lot, right? It's a sliding lattice scale to make them kind of quantum resistant, right? And so it's generating tons of tokens. It passes it in the very first SYN packet and then invalidates it. And then configurable, it then sends another token every 4 seconds after that. Okay. And then totally different token. They're all one-time use tokens.
Think about your, if you use a MFA tool of any sort, you get 6 characters for that 1-2-plan password. And then after a certain amount of time, you get another 6 characters. Now for MFA, it's 30 seconds. For us, it's 4. Yeah,
super lightweight, right? So it's just running the algorithm
same general concept
with the nonce, and so like I run this all the time on my iPhone. It never even shows up during the battery. It's super lightweight, and so it's just cranking out these, there's only 32 bits, I mean, 64 bits, but they're very small. Right?
Video was never read.
It's just streaming it in a memory pool, right? You can turn it up or down, depending on how much what you want your match rate to be and how much TCP retransmission. Because in a lot of modern stuff like direct satellite, the killer thing is filling your battery, right? You'll power down your antenna. So we want to keep it super lightweight. And then we also want to check in with the gray network. So if we're passing things like trust, and we'll get into that in the demo in a minute. So suddenly your trust level changes. By 60 standard, you should be checking every 10 minutes to see if an insider's credentials have changed, right? Or you've walked someone around the building. So if every 10 minutes, when that happens, what it does is it basically drops the pool on both sides and regenerates them. So that now you've picked up the new trust level. It's all configured.
Yeah, I wanted to add one piece. In 2011, we got a patent on video encryption, where you're dealing with large block allocations of constantly persistent IP connections over IP-based video links. So the technology that we used was that we embedded our encryption algorithm in the option bits of the IP packet, which meant that from a security standpoint, I didn't have to do deep packet inspection at my firewall level of the entire TCP/IP packet, nor did I need to encrypt all of the packets. I use randomized sequences to identify whether the parity of the cryptography that was embedded in the option bits was still valid or not. And so I randomized the sequence for how that was done, but I did not have to do the full packet inspection of every packet. This is the same kind of technology. So then when Brendan and I were talking, and he goes, "Oh, well, this is my process." I said, "Oh, okay, I understand this. But this is the way that you create lightweight traffic over persistent, always-on type of technologies. And the reason why the technology is so symbiotic is because we're leveraging the option bits inside of the IP packet instead of having to do packet evaluation, packet encryption, and packet sequencing of the whole IP packet."
Yeah, that's exactly right. The reason it's so lightweight is not the generation part, it's the transmission part. So all we're doing, so we do replace the sequence number, right? But some other applications like the Wi-Fi router in this room, does sequence
Brendan,
writing.
yeah.
So then we can trip it down to hide in the options field and an unused options field.
Yeah, Brendan, he has a question, right?
All right, I'll get to it in just a second.
Okay.
But what we're doing is we're replacing 32 bits that already exist in every packet header with 32 bits. There's no encryption on the tunnel, right? The Black Pearl does that. Our product does not. And so you have no incremental overhead on the transmission itself. And then all you have to do on the receiving end is look at less than 5 bits, to see if it's our product. Right? Immediately, you're going to know that's not in the token pool. So, because we don't have to decrypt, especially something modern like hybrid, there's no time on the compute side to encrypt and decrypt, which is the hardest thing you can do on a CPU. And therefore, it works instantaneously. So it's super lightweight. And you can run it on fast-moving mobile assets and wireless NASI networks without increasing any latency on either side. And that's why it doesn't bring it back.
So I'm guessing you still want to have it behind regular firewall. Could be susceptible to like denial of service.
Well, that's very interesting. So, yes. And no thing I'm saying you should turn off transport encryption and these. Right?
Oh, sure.
So leave all that stuff on. If you actually block, if you put it in front of your firewall,
Then
it
you
will
can
block
the
it off.
edge, right? Fuck, that's-
Yeah, when we talk to specifically, we've been talking to the Marine Corps about this. How to protect their bases from SCADA system attacks, right? But the problem we talked about with them is, hey, let's say you encrypt the heck out of everything and put it, quantum resistant. Not only do you need to run that software, you got to go out and replace all those edge firewalls with new hardware because this stuff is 10 years old and it doesn't have the power to run the new software. But if you put a tiny little device, and it could literally run on a Raspberry Pi, because it does a thing called dynamic blacklisting. So if you hit it with a DOS attack, on the SCADA edge, you're not going to get a distributed DOS attack. You're going to get it from a flood, a SYNAC flood from one address. It immediately blacklists. Missing a token, blacklist. And so it just sheds those packets and lets the ones with the token through. And so it actually confront an old firewall to shed a DOS, not a DDoS attack, but a DOS.
Actually, so I'll give you an example. Actually, but I think it could do a DDoS attack. So, but I'll tell you why. So, so one of these kids, so I've got the most lifespan with this technology. We had a use case with the Army way back when, where soldiers in military theater would get injured, and the doctors, the medics were writing the diagnosis on the soldier because enemy combatants were hammering the VPN concentrators that they were sent to, so they couldn't send their diagnosis ahead of schedule, before the soldier got there. And what we found is that if we put one of our gateways, and Brendan mentioned physical in this case, in front of that, dropping everything but the identified traffic from the field tech, that would come through. And what we were doing is alleviating the CPU utilization of that firewall. It didn't have to deal with all those things that it would normally block, because that's what the forward firewalls do. It only dealt with what got through our gateway, which it was supposed to do. So we alleviated the load, let it do what it was supposed to do, and then got, in this case, the medical diagnosis through it. Now, as Brendan mentioned, we'll black off, so if we start getting from certain IPs, a bunch of stuff, we'll blackhole you, we'll blackhole you, we'll just keep doing it because we're protecting ourselves. And it's a back off that goes with that. So it starts off with at a lower number and it will keep going. Eventually you can be blocked out for weeks on end if you keep attacking. So because of the intelligence we put into it, it can, I've never seen a DDoS attack that has succeeded against our technology. And I've done a lot of the proofs, proving grounds and et cetera. I'm not saying that it couldn't be done. I've just never seen it done. And I've been doing this for 15 years.
And because it's a one-time step, it blocks all forms of now and middle attack, but also side channel attack, keep track of it. So like you take an old firewall, generation 1 firewall, right? Remember, SCADA systems are measured in human lifespan. It's 20 years old. 80% of the stuff on an 80 base is 20 years old. So it's not new hardware. So there, you just hit it with a DOS attack until you forward down to the server. You steal the session key out of that using AI, out of the profile, and that's a memory attack, and then you just reinvent it. That will fail on our technology because it's a one-time. So that's the beauty of it. Now, I think we got to move on because we tend to talk a lot and not demo enough. Any other questions on cloaking? Because then we're going to talk about, microsegmentation related.
Okay, let's go ahead.
You want to go straight there?
Yeah.
All right. So I'm going to just pull up. So in your packet, by the way, this is what you see on the table. This is the network setup. We kept it very small, very flat. One thing we're doing so that we can do this demo is we're pumping the encrypted logs to Amazon to Graylog because we need, to show you anything historic, we needed multiple environments to come in and contribute to the big data, or else it would be a very boring demo. Now, you want to explain this at all?
No, we've already talked about it.
Okay. So do you want to go through the Black Pearl stuff, or do you want to talk about overlays?
No, let's talk about the overlays. Let's jump straight to the overlays.
Great. So let's jump through these slides.
What we're doing is this is a demonstration that we went through earlier, and we won't repeat ourselves, but this basically explains the functionality of how a gray network able to use an untrusted black device to be able to transmit information through the Ziva gray network and have connections that enable you to build a secure tunnel between an untrusted black device to a SIPR network. And it basically describes the traversal path of how networks go, and this is the end result. The end result is a secure outer tunnel and an inner encryption tunnel of VPN traffic that gets routed from a secret network to an unclassified, untrusted device. Does anyone have any questions about or understanding of what this technology is for CIFC? There's a lot to it. But what it is it's the NSA reference model that enables you, and as Jean, you can maybe say, it's an NSA approved technology that's very prescriptive and it's been proven to work. But we don't want to just say, and then the magic happens. We're using this to describe what is the process. Do you have any questions about how the NSA CIFC package and how it processes work? It's basically, if I wanted to kind of recap, it's a thing which is called an outer encryption tunnel, where you have an inner VPN, and you're using multiple layers of encryption that are provided from two different sources, but the black pearl is almost like it can't do anything without the mothership letting it know and giving it its approval to do what they do. You have any questions? I can maybe, okay. What about you? Do you have any?
No, we'd have to spend like 5 days.
Well, so here's the plug. We have a trusted integrator training workshop that we're actually doing teaching and instruction on how to build these secure gateways. And we're currently doing some training for the Department of the Navy. And we brought in 12 systems integrators last month from some of the top names that you probably already know. They are here to get expert level of instruction on how to configure these secure gateways. So let us just blow through, because we do know that that's a lot.
Otherwise, here in this cyber range.
Yes. Okay, so do you want to talk about the Invisinet reference architecture, or did you want to
Yeah,
jump?
just go to I'm just going to set up the overlay part. Keep going. Okay. So we talked about cloaking, right? Now let's talk about how you use identity-centric routing tools, right? And so when you see us redirect or forward or move traffic, keep in mind, not only can we change the pathways dynamically and programmatically, but not only would you have access to a new path, you would be completely blind to the other paths. Like if you can't get there, you definitely can't see it. But what we're doing is we're picking this up, right? So if we're going through Ziva to get to WidePoint, then in their secure database in the gray network, we get a lot of attributes of identity, right? So when you hit that control server, so anything that we're making routing choices of, we have in memory and we carry it along in our token. But we can, in real time, with a very secure tunnel to that server in your enclave, we can extend that to about 30 different attributes of identity, okay? And the same thing with things. So like if you have something like an Azure IoT hub labeling your endpoints, then we know, hey, that's a secure camera in this room using this software, right? So we know all that and we pass it through, and then we can build rules in our gateway, which we're going to demonstrate, that are identity centric. I mean, basically everything comes down to, forward, drop, or NAT, but we're doing that based on time of day, geography, identity. Now, in the gray network, as well as in things like OpenID Connect, everything in Zero Trust is about least privileged access. And trust levels are passed in these databases programmatically. So, whatever your identity system is, so we wrote this in the DoD standard in 2020. It's actually directly quoting up the system out, and we'll show it to you. We set up a trust level at the system level per gateway, at the group level, which can be programmatic change, and at the user level. The user level is fed into us, right? And then what happens is it's lowest common denominator. So everything has a trust level between 0, meaning lock everybody out, and 7, meaning secure, but less secure than 0. And so whatever the lowest number is, because it's least privilege access, that's what's going to allow through or block. Okay. And you can, there's 200 different interfaces of this thing. So if you have some other external system, somebody fails some kind of check and they're suddenly less trusted, we can get that triggered to us and we can encapsulate that traffic and move that person to a honey trap. Or they could have access to 5 endpoints and suddenly they can only get to 3 because they might, they might be trusted, just less trusted. So that's all happening in the background dynamically. Go one more slide.
Okay, we want to get to the second demo?
Yeah, right now.
Okay.
So then the last thing is if you overlay this into a SCADA system architecture, if you follow the Purdue model, your network should be partitioned this way. Now, I've never seen a network correctly set up this way, but this is the goal using, the standards. So you'd have a public DMZ with 2 sets of firewalls, then the IT systems and the BSS systems here, and then you have another set of firewalls, and then you'd have your SCADA systems, right? Pretty much all networks should be designed this way. So we would go in and deploy these gateways, and you can chain them together where you set it something like a 5. And then on the database themselves, you could lock this down to a 1 or a 2. And then this one's more restricted at a 2. So you generally set up the system trust statically. You can change it programmatically. And then the enforcers are more restricted. So you're funneling this through. And then typically what you do programmatically is change the group policy level. So I want to allow a authorized vendor to do a firmware update to this machine from midnight to 1 a.m. So what you would do is programmatically hit it through a ticketing system like a ServiceNow and say, Brendan Sullivan in manufacturing A can be in this system for 30 minutes. And then boom, the moment it hits that timestamp, this becomes visible to that person using their tokens that is keyed to them, and they have access. Clock strikes 30 minutes later, they're kicked out. Okay, so that's programmatic micro segmentation where you can get per user, per device, per protocol, per session to an endpoint. That is super granular. Okay.
All right. You want to move to the next demo?
Yeah. So next demo. So on the phone, we have Kevin that's sitting here patiently. I'm going to have him grab the screen. He's listening to us. And what he's going to do is we're going to walk through the gateway. He's going to drive while I speak. I'm going to show you the rules. And then we're going to actually show you it doing microsegmentation in a demo through the SIM. So Kevin, if you'll, I got to pull up Teams so you can see him. There you go. If you'll grab the screen and I'll make this full screen. So right now he's in the Invisinet gateway. That's the gateway sitting on the spots. Okay. And Kevin, if you you can't hear him on my speaker, so I'll do the talking. It's like a puppet show. So Kevin, will you go to the configuration screen and show us the trust level rules? Okay. So like I mentioned, we just set up very simple rules. And at this thing, I set all the trust levels the same, system, user, and group, because I want to show you by group, you can change the behavior, even if all trust is equal. So we've set up 2 users, Kevin and I. One of us is in manufacturing A, one's in manufacturing B. We have similar trust levels, but one manufacturer can see the resources and one cannot. Okay, so he's now going to the rule here and hit edit on this rule. So this is the type of rule you'd set up. Now, of course, we have a UI, but in a big network, your network configuration tools would just do this programmatically. Like you would probably not use our UI. It's not designed to that, but small maintenance, yes. But this is all programmatic through multiple levels of interfaces. So we have about 200 different interfaces to hit this with triggers. But as you can see here in manufacturing A, everything is set by trust level. So you first set level 5 rules. Okay, and then it says manufacturing A getting to this protected Linux server. So there's a map of the CMDB. I want to get this thing. I want to allow manufacturing into this thing by forwarding it through the gateway and letting it get to that resource. You can have app lists You could have protocol. So if you only wanted to block UDP traffic or not let them download a file or not SSH, you can do it at the protocol level. Okay. And then that's how you trigger these rules. Now, Kevin, if you will, and so if he goes, hey, go to the Invisinet point and just show the people that are against this. So now we're reading this in from the identity system, but like right down here, if he scrolls down, you'll see my laptop, and then I'm assigned to, to manufacturing A. So that's me reading on the user side of things on the agent side, comparing it to the gateway rules at a group level. All right, Kevin. So now pull up the SIM and start generating some traffic. So it would be very boring if I just went to a web browser and clicked on it, because we'd have to wait 15 seconds for it to time out. But because this is all logging in real time, to watch it in the SIM, which is what we're doing. So right down here is Kevin's Mac client. Okay. Turn that off for a second. Now, normally this would run in the background, right? But for the purpose of the demo and the way iOS works, it looks like a VPN, but it's not. So now activate it. So when he activates this, so he's running continuous pinging between these two servers. And when he activates this thing, it's going to go green here in just a second. I hope.
It's been green for 20 minutes, so of course now it's not.
Yeah, it's curse of the demo. There we go. So when it turns, oops, there we go. Went green. When it turns green, his token generation is, there we go. So what he's doing on either side is there's two resources, right? 008 and 009. We're using the inside address of these things. Oh, so he's routing through this gateway up to Amazon and hitting some web pages. He's running a port scan on port 22. Okay. Now, what should happen, by the way, we configure these rules is the guy that's in manufacturer A group should get to one server, but he should be blocked by the other. It's all doing that by enforcing the rules based on his identity. So now go back to Graylog here, Kevin. So here it is, right? Here's 008 and the manufacturing group. So this server over here, he can get to in this group. This server over here is getting blocked and discarded. If you looked at the responses of this 15 seconds later, it will say host not found, IP address. It will do all the cloaking tricks that Doug just showed. It's all outputting it to whatever your SIM is in real time. Okay. Now, Kevin, go and open a record. So we've put there's no other logs other than our agent running in this environment. So there's no Cisco or anything enriching this. This is purely a single record outputting. And then drill in. So you can see the source and the destination. You can see that it came from Kevin's laptop on Invisinet's domain. Okay. And the gateway is turned on in enforcement mode, so it would actually block it. So if we want to run this thing so we have another mode called monitor, where what it does is it interprets all the rules and it would alarm, but it won't actually block the traffic. So if you wanted to have a hidden audit trail, but it enforces nothing, that's what monitor mode does. It's saying this should be blocked. This is an intruder, and it's throwing it hidden to the SIM. Okay. Because remember, if you chain these things together and you hop here, 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 and here, and you do a replay inside of Graylog, it will draw you a map of how this user got here. Okay. And then it interprets the rules in real time to enforce this. Okay. So that is a showing identity. Now, you can enrich this and hit in real time the secure server and find the other 35 attributes that you want to know about this person. Like when's the last time their clearance was updated? Whatever you know about that user, you can hit this in real time from the SIM. Okay. So that's how and then you can do moving target defense. You could do time of day. You could do geography based. Hey, this vendor can get to these systems. This vendor could only get to this zone. I'm gonna grab back PowerPoint for a second, Kevin. Let me stop here and see if you guys have any questions. I'm going to show you insider threat detection, which is very, very hard to demo. So I'm just going to show it to you in PowerPoint. So what would happen now, back over here, is, I think Darnell shut our PowerPoint down. It's okay. I'll just reopen it. There we go. All right. So last slide. So let's go to this. So now imagine this scenario. Okay. You got two DMZs and you got a really secure database over here. Okay. And over here, I've got an actual authorized guy, but his trust level is 4. And then here, no token. This is an external threat. Okay. What happens if suddenly these guys show up at either one of these databases, right? How did they get here? Well, they either got here because IT made a mistake and there's some path that gets around this gateway. And that happens all the time. I see it in casino sets up, that's just bad hygiene at the network layer. So the good news is if the enforcer's in enforcement mode, they still can't, they hit the NIC and they're still blocked. It will instantly alarm, right? But the question is, how the hell did they get here, right? Because the guy with a trust level 4 should not have gotten through the gateway at a trust level of 2. That's more restricted. So that means either IT made a mistake, this guy has escalated privileges through some hack, or you were already compromised, right? This isn't an indicator compromise. This is an absolute certain that you're compromised, right? And so what you would do is throw an alarm, send that to your SOC analyst, go research what's happening, either get IT to fix the hole they created in the network, or kick the user out and refer it to your cert. From an audit compliance, you got a year's worth of logs. You could run something like, hey, this is a zone 2, like a SCADA zone, security zone that I created dynamically as an overlay. Well, look, in the last 30 days, and we're doing this for NIS2 compliance, which is in Europe for manufacturers with the 10 million euro fine. This is what the CISOs need to save their lives and their jobs. But you've looked at these in real time, but in the last 6 months, there was 6 events where this guy got into this zone. For the ones with no token, that's unknown user missing. That's really bad. Or, hey, there's a zone 2 violation. This user, Chili1, my boss is named Chili. So he got into this zone and he does not have the right privileges. So that is a zone 2 violation. Okay, very simple report. In Graylog, there's about 100 different zero trust IAM reports that just how the box would work. Most modern SIMs have this kind of thing, so it's very easy to. So we just have a very standard key value pair syslog where you don't even need a program. You just plug it in and map it to the right charts, and you're up. So I'm just using WidePoint because they're Houston-based. They're partners of ours. They're writing all the dashboards for us for demos. And they work in the mid-market for like oil and gas. So that's how so that's the continuous monitoring, both threat alerting as well as, regular scanned audits. All right. Yeah. Okay. That's it as far as demos go. What questions can I answer for you?
I think the next steps, because as we talk about it, there's a lot of information to unpack, and if we don't feel ourselves over the course, we might live enough to have our next demos. But I think what we want to do is we want to align the proof of concepts to the specific use cases, to the environments. We have one that's going to go on, and because we're not necessarily on record, because this isn't the DISA meeting, but for those people, the pilots that we currently have in play, is that we're working with the University of Maryland Global Campus on a pilot program for being able to deliver classified training from a remote on-period, where this is actually going to be what's known as the mock reg network, which is the classified network. So what happens is that from upstairs, we're going to, from the TAC, where there's a data center, It's on-prem, they're gonna be simulating the red network, the SuperNet. And they'll be monitored and on-place specifically for the DoD specifications. And we have an in-place gray network that's currently being built out at Viva Network, at Viva headquarters, the next gen ID. So the black network is here in this environment, and we're building this in the format of a cyber ring. So that we'll be able to compose architectures, run scenarios, and compose them in whichever way that we can do by using digital twins and similar architectures that we can run against this network to validate security posture, to identify the IPM compliance, and how it maps to the NSA system capability very explicitly. So, if this was phase 2 of a next step process, the next thing that we're doing, that we're working on, is an IoT proof concept for the seaports, and the other is for remote training. If you have a POC that you would like for us to put together for you, we have the architecture and the infrastructure here to compose whatever that cyber ring would be. And we'll be able to build it and we'll be able to test it. So where this isn't the end all be all, Rome wasn't built in a day. But this is the foundational aspect as we continue to go through certification and validation. Invisinet is part of our sponsor. They've been working along with us. We're in the process of getting the educational partner agreement, which should be executed within the next couple of weeks, with the University of Maryland Global Campus. And then afterwards, we're in the process of working on, if need be, a CRADA agreement, cooperative research and development agreement with DISA, so that we have the access to the people from DISA to prove out our technologies, to get technical assistance, to have them to come in to do their third-party validation. But more so, they're already sponsoring us for our first proof of concept. So once you're in, you're in. So as long as we can continue to compose some solutions, then that'll be fine. But what we're looking for is the proof of concepts and potential capabilities to field live tests within each one of your organizations, so that we can demonstrate a real world problem. One of the comments that we said earlier was your technology fixes a lot of things that we've been trying to fix for a while.
Yeah, and then in the enterprise space, right? Some summer demos, public demos we're going to do. We would absolutely like federal government partner and use cases from certain missions. But more publicly, I'm flying to London after this. We've been working with Viasat, to embed this in the Viasat 3 satellite terminals as a hidden layer. We're going to announce at the World Maritime Organization, the Inmarsat conference, which connects all the ships, APSC. And that is to do satellite protection. So we're doing a trial in Italy with the European Space Agency and Telecom Italia. And it's for autonomous surface shipping called 5G Max, which has been funded by the European Space Agency for the last 5 years. What they want to do is, when you look at these busy ports, these guys sit, for days at anchor waiting for the pilots to come on board to pilot it in. And when you get to a busy port over satellite, it loses its resolution. It's a big problem, and the networks kind of suck offshore. So Telecom Italia has refitted their 5G signal so they can now throw it about 3 kilometers across the opening of the harbor. And they want to be able to, from a control center, remote pilot in the ships. And at the same time, they want to burst transmit all the manifests of the cargo containers so they can speed up the loading and offloading and the customs and look for piracy on board ships at ports. That's a part of port security. The technical challenge here is you got to get to the port to get a 1 gigabit connection to actually remote pilot the ship. And you need a lot of network to have all the LiDAR, radar, all that. You really want to, about 10 miles out, you want to be transmitting positioning, on-time arrival, 6 levels of GPS, like micro positioning. So they're just going to drop down to an Invisinet protected thing over those satellite links, over Starlink. Almost all those ships are moving to Starlink because, we need to set that up. And as you approach the port and and then you can get onto the 5G, dynamically, then it kicks in the inner outer tunnels and starts a 1 gig connection to bring up the piloting speed. Okay, so you can kind of see it's trigger based and it's increasing that those L-band networks can't handle that form of encryption.
Start moving toward the autonomous cargo and cruise ships.
Yep.
That we want to, that also need to be highly protected.
Yeah.
And drones.
Yeah.
That we're going to need lightweight encryption capabilities that Invisinet provides. To the back. Okay.